Good morning, students. I'm Dr. Ramurthy Reddy, Assistant Professor, SU Engineering College, Tirupati. In last class, we have discussed Cauchy integral theorem, Cauchy integral formula, Cauchy generalized integral formula, Liveless theorem. And in today's class, we will discuss the expansions, Taylor series expansion, Laurent series expansion, and some definitions, singular point, isolated singular point, essential singular point, and pole. The Taylor series expansion is exist if f of z is analytic at all points. So we know that the Taylor series expansion of f of z is f of z equal to f of a plus x minus a by 1 factorial f dash of a plus x minus a whole square by 2 factorial f double dash of a plus and so on. So this is your Taylor series expansion of f of z when it is analytic at all points. If you put a equal to 0 in Taylor series, you get another series which is called Maclaurin series. See, f of z equal to f of 0 plus x by 1 factorial f dash of 0 plus x square by 2 factorial f double dash of 0 plus and so on. So this is Maclaurin series which is obtained by put a equal to 0 in your Taylor series expansion. See some standard expansion series expansions which is e power z equal to 1 plus z by 1 factorial plus z square by 2 factorial plus z cube by 3 factorial plus and so on. So that can be expressed as summation n equal to 0 to infinity z power n by n factorial for mod z less than infinity. So this is in terms of summation notation. So for checking, so put n equal to 0. If n equal to 0 means z power 0 by 0 factorial which is 1. So first term. So if n equal to 1, z power 1 by 1 factorial which is second term plus and so on, right? So similarly sin z, so this is z minus z cube by 3 factorial plus z power 5 by 5 factorial minus z power 7 by 7 factorial. So which is powers is all are odd. So minus 1 whole power n, z power 2n plus 1 by 2n plus 1 factorial. So similarly cos z, so 1 minus z square by 2 factorial plus z power 4 by 4 factorial minus z power 6 by 6 factorial and so on. Sin hz, so in place of sin z, replace negative by addition. So z plus z cube by 3 factorial, z power 5 by 5 factorial and so on. Similarly cos z. So this is your expansion. It's very important. 1 by 1 minus z. So that can be written as 1 minus z whole power minus 1. So that is 1 plus z square plus z cube plus and so on. So similarly 1 plus z whole power minus 1. So which is alternatively plus and minus 1 minus z plus z square minus z cube plus and so on. So this is alternative. So these two series expansions are very important for Lorentz series expansions. So of course Taylor series also. So these are standard expansions. So which can be obtained by using Taylor series. See, so this is e power z about z equal to 0. So that means f dash of a, that means f dash of 0. Since e power z is everywhere differentiable, so its first derivative, second derivative and so on all are e power z only. Then e power 0 is 1. Now f of a is 1, f dash of a is 1, f double dash of a is 1 and so on. See, expand e power z as a Taylor series about z equal to 1. Taylor series about z equal to 1. Now given f of z is e power z. So we have to find Taylor series. So Taylor series expansion of f of z e power z about z equal to 1. So about z equal to 1 means, so let us assume z minus 1 as w. So this is simplest way. Otherwise you directly substitute f of z equal to f of a plus x minus a by 1 factorial f dash of a plus and so on. So that's also good. Or otherwise, so z minus 1 equal to w. So this is easiest way. Now f of z is e power z. E power z can be converted as e power 1 plus w because z is 1 plus w. So which is a power m plus n is a power m into a power n. Now e into e power w. So this is constant outside and the e power w. So we know that the expansion of e power z 1 plus z by 1 factorial plus z square by 2 factorial plus and so on. So this expansion is valid in the reason is for all w. So that means everywhere it is analytic, everywhere it is exist. Now at last substitute w equal to z minus 1. So then it is a Taylor series expansion about a point z equal to 1. So it exists for all z minus 1. See second problem. Expand f of z is sin z. So about z equal to pi by 4. See Taylor series expansion of f of z at a point at a point a is given by f of z equal to f of a plus x minus a by 1 factorial f dash of a plus x minus a whole square by 2 factorial f double dash of a plus and so on. So where a is nothing but pi by 4. So f of z is nothing but sin z. So you have to find f dash, f double dash, f triple dash. Right? So sin z is so your f of z, right? F of pi by 4. So this is your Taylor series expansion about a point z equal to pi by 4. Now you need to find f of pi by 4, f dash of pi by 4, f double dash of pi by 4 and so on. Right? Now since f of z is sin z, f of pi by 4 means sin pi by 4. So sin 45. Sin 45 degrees is 1 by root 2. See f dash of z. So sin z, derivative of sin z is cos z. So then derivative of cos z is minus sin z. Derivative of minus sin z is minus cos z. Then you substitute. So sin pi by 4 which is equal to cos pi by 4. So which is 1 by root 2. So then you get this. Now directly substitute these values in your Taylor series expansion about z equal to pi by 4. See, expand f of z equal to 1 by z square minus z minus 6 about z equal to root the minus 1, z equal to 1. Now you consider f of z is, so this is your f of z, and using factorization method, z square minus z minus 6 can be written as z square minus 3z plus 2z minus 6. If you take z as common, if you take minus 2 as common, then you get z minus 3 into z plus 2. Now this is your f of z. So now you need to split this function. So using partial fractions. So which is 1 by z minus 3 z plus 2. So which can be written as a by z minus 3 plus b by z plus 2. See, so when in Taylor series as well as Laurent series, the partial fraction is very important. So if it is linear, directly you put a by that linear factor. If it is square, az plus by, so that's a square factor, right? So these are linear factors, so that a by z minus 3 plus b by z plus 2. Then your LCM is, here LCM is z minus 3 z plus 2. Now a into z plus 2 plus b into z minus 3. So LCM, this term get cancelled, then you get 1 equal to a into z plus 2 plus b into z minus 3. Now you put z equal to minus 2. If you put z equal to minus 2, this term is 0. Then here is minus 2 minus 3 is minus 5. Minus 5b equal to 1. That means b equal to minus 1 by 5. Now similarly put z equal to 3. This term is 0. So this term is 0. So z equal to 3 means 3 plus 2 it is 5, a equal to 1. A equal to 1 by 5. Right? A equal to 1 by 5, a equal to 1 by 5. So that can be written as 1 by 5 into 1 by z minus 3 minus 1 by z plus 2. Now see, about z equal to minus 1. See, about z equal to 1. So about z equal to minus 1 means z plus 1 equal to w you take. Here z minus 1 equal to w you take. See, now we have to expand f of z about z equal to minus 1. So that means z plus 1 equal to w. So implies z can be written as w minus 1. Now f of z is 1 by z into 1 by this w minus 4, w plus 1. So here is, so we have expansions of 1 by 1 minus z or 1 by 1 plus z. So that I am taking minus 4 as common, then 1 by minus w by 4. Right, here is 1 plus w. So then it is 1 by 5 into minus 1 by 4. So this can be taken to numerator, which is 1 minus w by 4 whole power minus 1. minus 1 plus w whole power minus 1. So this expansion, series expansion is we know. So which is 1 minus x whole power minus 1 is 1 plus z square plus and so on. Right, 1 plus in place of z w by 4 plus w by 4 whole square plus and so on. So we have to know that this series is exist when mod z less than 1, right? So here is mod w by 4 less than 1. So this series is expansion when mod w by 4 less than 1. So this series is expansion is valid when mod w less than 1. So here is mod w by 4 less than 1 means mod w less than 4. It is mod w less than 1. Mod w less than 4, mod w less than 1. The common reason is mod w less than 1. So that total this series is exist for mod w less than 1. See, this is mod w less than 4. This is mod w less than 1. The common reason between these two is mod w less than 1. So at the last you substitute w by z plus 1. We required. So this is your required Taylor series expansion. Right, so in place of w z plus 1 less than 1. Now similarly, so we have to expand f of z about z equal to 1. So put z minus 1 equal w, z equal to w plus 1. F of z is 1 by z into 1 by w minus 2 minus 1 by w plus 3. It is 1 by 5. So here you have to take minus 2 as common, right? Here 3 as common. Now see, 1 minus w by 2 whole power minus 1 if we take it as a numerator. So this is also we take numerator as power minus 1. Minus 1 by 2. So this expansion is valid when mod w by 2 less than 1. That means mod w less than 2. Right? So you note it, mod w less than 2. Here is mod w by 3 less than 1 means mod w less than 3. The common reason is, see, I mentioned the reason also. Reason also, mod w less than, since the common reason between these two is mod w less than 2. Right? Now substitute z minus 1 as w. Then you get the series. Right? So the next one is Laurent series. See, let C1 C2 be two circles with two radius with R2 less than R1. Z dash is any point on C1 and C2. Let f of z be analytic on C1 and C2 throughout the region between two circles. Z is any point on the shape. Then, so this is your analytic part we say. So this is principal part. So where an and bn are. So what is the difference between Taylor series and Laurent series is, in Taylor series we have only positive powers of z, whereas in Laurent series we have negative powers of z also. So for that, so this is power n, so that means it is analytic part, it is a Taylor series part. So here is z minus a whole power minus n, so it is negative part. This part is called principal part. This is analytic part and this is principal part. So in Taylor series we have only analytic part. In Laurent series we can have negative part also. Right? See, expand this in the region this and this. Right. First you have to split. So using partial fraction. So that is 1 by z square minus 2z minus z plus 2. So that is your factorization, and taking z as common and here minus 1 as common and z minus 1 z minus 2. So this is your function f of z, and this function so can be split by using partial fraction a by z minus 1 plus b by z minus 2. So now, so taking LCM and cancel it, 1 equal to this and this. Now put z equal to 2, it is 0, 2 minus 1, it is 1, b equal to 1. Now put z equal to 1, so it is minus a equal to 1, a equal to minus 1. Right? So this is your f of z. Now only singular points are 1, 2 are singular points. Function f of z is given, this is given region. So what they given is 0 less than mod z minus 1 less than 1. So that means if we take z minus 1 as w, so that is 0 less than mod w less than 1. See here, 0 less than mod w less than 1. See, 0 less than mod w means it mod w is greater than 0. So it is always positive. Mod w is greater than 0. And the next one is mod w less than 1. Next one is mod w less than 1. Now in this region you have to expand the function f of z. So this is your function. Since mod w is greater than 0, so we leave this term, and here is taking minus 1 common, 1 minus w, so it is 1 minus w whole power minus 1. See, mod w less than 1, so this expansion is valid when mod w less than 1, so that 1 plus w square plus and so on, it is minus 1 by w. See, this is a analytic part, positive power, so it is negative power, principal part. So in Laurent series we have analytic part and also principal part. So this expansion is valid when 0 less than mod z minus 1 less than 1. Now next reason they given 1 less than mod z less than 2. See here. So first you split this has two regions. 1 less than mod z. 1 less than mod z means mod z is greater than 1. Mod z is greater than 1. See here. 1 less than mod z means mod z greater than 1. Or z you take left side, that means 1 mod 1 by z less than 1. So that means in the series expansion of f of z you take z factor z as a common, so 1 by z, then you get 1 by z here. So it is directly mod z less than 2, mod z less than 2, that means mod z by 2 less than 1. So in your series expansion, so expansion exists when mod 1 by z less than 1, when mod z by 2 less than 1. So now f of z is this, and the first in the first term minus 2. See here, check mod z by 2, you need to get mod z by 2, mod z by 2. So mod z by 2 means you take minus 2 as common outside, minus 2 as outside. So otherwise I'll take minus, only minus as common, then it will leave it. Then 1 minus z by 2 you are getting, right? 1 by z you need to get 1 by z. So taking z as common, then you get 1 by z, right? So it is minus 1 by 2, it is minus 1 by z, and this is power minus 1, power minus 1. The denominator will go to numerator, so its power is negative, right? So this is, we know that the series expansion 1 minus z whole power minus 1, so that means 1 plus z square plus and so on. So in place of z you have z by 2, it is z by 2, it is z by 2. Here minus 1 by z, it is 1 plus 1 by z, 1 by z whole square plus and so on. So this expansion, first term expansion is valid when mod z by 2 less than 1. Now second one is valid when mod 1 by z less than 1. Then you write this term as in terms of summation notation also, minus 1 by 2 into, so this is summation equal to 0 to infinity, in place of z by 2, z by 2 whole power n. So this is also minus 1 by z, it is 1 by z whole power n. So 2, so that means a power m into a power n is a power m plus n, so minus of 2 power n plus 1 here. Here is 1 by z power n plus 1. Next problem, expand f of z equal to, so they given a function in the region 3 less than mod z plus 2 less than 5 by Laurent series expansion, right? First you have to split them, now using partial fraction. So since all are linear factors, a by z minus 1, b by z minus 3 plus c by z plus 2. Now put z equal to 3, this a is 0, multiple of a is 0, and z equal to minus 3, 3 na, it is also 0. The only b term you get, 3 minus 1 is 2, 2 into 5, 2 into 5, so left side is 3 square 9 minus 18 minus 1. So 9 minus 18 minus 9 minus 1 is minus 10, it is 10b, 10 10 get cancelled, b equal to minus 1. Now put z equal to minus 2, so this term is 0 and this term is 0, you get c, minus 2 na, minus 3 minus 5, minus 3 into minus 5 plus 15, 15c equal to, so this left side is 4 plus 12. 4 plus 12 is 16. 16 minus 1 is 15. 15, 15 get cancelled. C equal to 1. Now put z equal to 1. So this term gets 0. This term is 0. Then 1 minus 3 minus 2. 1 plus 2, 3. So that means it is minus 6a. Here is 1 square 1 minus 6 is 1 minus 6 is minus 5. Minus 4, 5 minus 1 is minus 6. 6 6 get cancelled. A equal to 1. Right? Now here I am explaining. Right. Alright, these three items you now see the reason, coming to reason, 3 less than mod z plus 2 less than 5. So that means you take z plus 2 as w, then your series is of the form z plus 2 as w. So then 3 less than mod w less than 5 your region. So this can be splitted as 3 less than mod w and mod w less than 5. That means 3 by w less than 1 and mod w by 5 less than 1. So in your series you get these two terms. Now put z equal to w minus 2. So then your series will becomes this. Then now 3 by w you want. 3 by w you want if you take w as common. W common 1 minus 3 by w. Next here 5, w by 5 you need to come. That means taking 5 as common. That means minus 5 as common. So you series like this. Then so we have the expansion 1 minus z whole power minus 1 expansion 1 plus z square plus and so on. So here also same formula. In place of z you use 3 by w. In place of z you use mod, w by 3. So this 1 by w is it is put same like that. So then this is so after your series you substitute w by z plus 2 in terms of z plus 2, then you write in terms of summation also. So give two Lorentz series expansion in powers of z for f of z equal to 1 by z square into 1 minus z and specify the region in which these expansions are valid. So you need to find a Lorentz series and you have to also specify the region. So in which region the series is exist. Now first using partial fraction split f of z. That means the function f of z as three singular points 0, 0, 1, right? The Lorentz series expansion of f of z can be obtained about z equal to 0. Right, you need to check the region. First you have to split a by z plus b by z square plus c by 1 minus z. Then this is your LCM. LCM this term get cancelled. 1 equal to a into z into 1 minus z plus b into 1 minus z plus c into z square. Now put z equal to 0 in the above equation. If put z equal to 0, this term get cancelled 0. This term also 0. Then b equal to 1. Put z equal to 1, this term is 0, this term is 0. And it is c equal to 1. Now comparing z square coefficient. So left side is 0. Here is minus a. Here is no. Here is c. Minus a plus c equal to 0. That means a equal to c. A equal to c means c value is 1. So therefore a value is 1. This is your series. Right? Now it is 1 by z. It is 1 by z square. So these are principal part. Directly it is in principal part. That means mod z is greater than 0. Mod z is greater than 0. That means 0 less than mod z. Then here you get the regions. So if we take directly it as 1 minus z whole power minus 1, then it is 1 plus z plus z square plus and so on. This expansion is valid when mod z less than 1. Here is 0 less than mod z. This expansion is less than 1. 0 less than mod z less than 1. This is one of the region. If you take minus z as common, it is 1 by minus z into 1 minus 1 by z. So that means 1 minus 1 by z whole power minus 1. So this expansion is valid when mod 1 by z less than 1. Right? So it is mod z greater than 1. So mod z greater than 1. So mod z greater than 1 means it is less than infinity. So this series the expansion less than 1, and the first two terms are not defined, so that 0 less than mod z, that means mod z is greater than 0. This is your f of z, and here I am taking minus z as common, 1 minus 1 by z, so 1 minus 1 by z whole power minus 1. So this is, after simplifying, you get for 1 less than mod z less than infinity. Right? So this is your Lorentz series expansion problems. So the main difference between Lorentz and Taylor series expansion is, so in Taylor series expansion you get only positive powers. So in Lorentz series you can get negative powers also. Now coming for definitions of singular. See, singular point. A point z naught at which f of z fails to be analytic is called singular point. So a point at which f of z fails to be analytic. Fails to be analytic means it fails to be differentiable. See, for example, f of z is 1 by z. So at z equal to 0 it is not defined. So therefore that point is singular point. See, 1 by z square at z equal to 0 it is not defined. It is singular point. See, 1 by z minus 2. So at z equal to 2 it is not defined. 1 by z plus 1 at z equal to minus 1 it is not defined. Those points are singular points. So to find the singular points you equate the denominator to 0. That's all. Now isolated singular point means there exists no other singular point in the neighborhood of that singular point. No other singular point. See, here I am taking f of z as 1 by z minus 2, z minus 3. So only two singular points, z equal to 2, z equal to 3. So in the neighborhood of that, that means 2 minus epsilon to 2 plus epsilon, 3 minus epsilon to 3 plus epsilon, there is no other singularity since epsilon is very small. 2 minus epsilon to 2 plus epsilon, there is no other singularity. So that means those points are isolated singular points. Now essential means an isolated singular point z equal to z naught is said to be essential singular point if Lorentz series expansion of f of z has infinitely many terms in the principal part. That means, so it has infinite number of negative powers of z, then that singular point is essential singular point. So next definition is removable singular point. So that means its principal part is 0. So removable. An isolated singular point z naught is said to be removable singular point of f of z if the Lorentz series expansion of f of z has no principal part. So or otherwise limit z tends to z naught f of z defined is not defined, but using L'Hospital rule you can find the limit, so then that point is removable. See here, so this is of course about Lorentz series. Otherwise see here, if a single valued function f of z is not defined at z equal to 0 but limit exists by using L'Hospital rule, then that point is also removable singular point. See, sin z by z it is not defined, but after getting limit z tends to z naught sin z by z is, you have to use L'Hospital rule, then you get the limit. So that singular point is removable singular point. Now we know singular point, isolated singular point, essential singular point, removable singular point. So in next class we will discuss pole. So what is pole? Pole of order m, simple pole, and residues, etc.